Hello, this video will be presenting a new method for reconstructing feet from images using surface normals and their uncertainty, named Found. Accurate reconstruction of the foot is a challenging task of key interest for the shoewear and orthotics industries. Existing methods for foot reconstruction fall into three categories. Some require either expensive scanning equipment or mobile phone sensors that are not available on all devices and are often tricky to use. Others use photogrammetry, recovery of shape from a large number of input images, that uses no prior knowledge of foot geometry when reconstructing. Finally, some approaches attempt to directly predict foot geometry from silhouettes. This loses a large amount of information from the images, as the occluding contour is the only useful information provided by each view. Our primary contribution is a 3D reconstruction method that takes multiple calibrated images of a foot taken on a mobile phone and uses predicted surface normals, keypoints, and uncertainties to reconstruct an accurate 3D model. Our method relies on synthetic data for training. As such, we release a synthetic dataset of 50,000 foot images, alongside our custom Python library used for rendering these images in Blender. Finally, to effectively evaluate our method, we release a benchmark foot 3D reconstruction dataset containing paired high-resolution 3D scans and calibrated 2D images. We build our synthetic dataset from 8 high-resolution 3D foot scans. We vary environment lighting, camera pose, and background to capture the distribution of images seen in real-world foot scanning processes. We render RGB, keypoints, surface normals, and segmentation masks. This dataset is crucial to our method. Capturing accurate surface normals for in-the-wild images is difficult, and so this method allows us to generate realistic surface normal labels at scale. We render with Blender using our custom Python library available now on GitHub. Next, we train a 2D normal predictor to run on real images. We follow previous approaches and predict per pixel both a surface normal and a corresponding uncertainty. As we are not concerned with our network learning the surface normals of image backgrounds, we set our background pixels to have random surface normals in the unit hemisphere facing the camera. When training on these pixels, we do not propagate gradients to the surface normal prediction, only to the uncertainty prediction. We obtain segmentations by thresholding our predicted normal uncertainties. We also train a 2D predictor to predict keypoint location, uncertainty, and visibility for the keypoints included in our synthetic dataset. We now have the tools we need to implement our found method. We start with a parameterized model introduced in previous work, the find model. This model is characterized by an affine transformation of rotation, translation, and scaling, as well as shape and pose embeddings. As input data, we have n image views with calibrated cameras. Here, we use our benchmark reconstruction dataset introduced in this paper, Foot 3D Multi-View, whose cameras are calibrated via Colmap. We run our 2D predictive networks on every image and then are ready to apply our losses during optimization. For registration, we use a keypoint loss, which, for every keypoint in every view, is the L2 loss between the 2D keypoint projection and the projection of the find model's keypoint. This is weighted by the predicted uncertainty and masked according to whether the keypoint is visible. For accurate surface fitting, we use our predicted surface normals. For every pixel inside the foot in every view, we minimize the angle between the 2D surface normal prediction and that of our find model when differentiably rendered. We weight this by the predicted normal uncertainty. Finally, we also use a silhouette loss, which is an L2 loss between the silhouette obtained from our thresholded normal uncertainty and the differentiable rendering of our find model. Using these losses, we optimize over multiple views. Here you can see the process for one scan, with 2 different views shown. We find that the keypoint prediction helps provide an accurate initial registration, and the surface normal loss guides accurate shape reconstruction. We show that our 2D normal predictor, trained only on synthetic data, significantly outperforms both photogrammetry and off-the-shelf normal predictors. Despite using only 8 3D scans, our aggressive augmentation pipeline has ensured that our predictor generalizes well to in-the-wild images. We show significant qualitative improvements over photogrammetry using Colmap. For 30 input views with a large amount of overlap, our method performs similarly to Colmap on chamfer error, a nearest neighbor vertex distance metric. Our method provides a more accurate surface, beating Colmap significantly on surface normal metrics. Our method outperforms Colmap when given access to a very large number of views. However, where our method really shines is in a few view setting. Below 15 views, Colmap fails to find sufficient overlap between images to effectively reconstruct. However, our model retains its accuracy with as few as 3 views. Our normal loss is critical for this, and the use of normal uncertainty helps to improve the accuracy. Please follow the QR code or URL to find out more about our project.